Greetings everyone, bumps, dips, and loops, oh my. This is a podcast that's just going to wrap up that circular motion challenge and go through some of the big ideas for what's going on circular motion wise when we're talking about a bump, a dip, or a loop. So let's look back at these examples of objects moving on a bump, a dip, or a loop. So as you go up the hill and you get to the very tip top and you start to change direction, remember as your body starts to go up the hill, it wants to keep going up in a straight line, but the car moves from underneath of it, and your body is going to have to start falling with it. So when that happens, we feel lighter in our seats. Okay, so when I look at a force diagram at this instant, because we are accelerating towards the center of the circle, that force of gravity has to be greater than the normal force on us from underneath. And so we feel lighter when that happens, whenever the normal force is less than the force of gravity. And so when I go faster and faster and faster, that normal force just keeps getting less and less and less. And at some point, when the normal force is equal to 0, then the centripetal force, or what's pointing towards the center of this circular path, is just equal to Fg. And if we keep going faster and go faster than that, common sense tells us that our car, like in every action movie you've ever seen, is going to go flying off. And when the normal force is equal to 0, at that speed, now we become a projectile. And when the only force acting on us is gravity, we call that a projectile. And so if we go any faster than that, it is not safe because we just turn into a projectile. There's that minimum speed when we can come down and go the rest of the way safely. When we get to the bottom of a dip, our body wants to keep going to the ground, but it can't. Okay, once our body gets going towards the ground, it just wants to keep going in that direction, but the ground gets in our way. And the faster we go, the harder we jam into the ground, and therefore the harder the ground pushes back on us. And so to keep a circular path, the centripetal force always has to be towards the center. So the normal force in a dip is going to be much greater than the force of gravity. And when we feel the seat pushing us harder than normal, we feel heavy. Okay, we feel heavier. And so there's no maximum speed here, unless you were talking about the maximum speed that your body could maintain that normal force from the seat. And then the most interesting of all is the loop. And the reason why loops are so popular in roller coasters is because when you're going through a loop, you can actually simulate 4 different feelings. You can feel normal, you can feel heavier, you can feel lighter, and if they design the ride correctly, you can feel weightless. And this all depends upon how fast we're moving. So as I'm going around, let's look at the forces. Let's say we're moving at a moderate pace. Okay, so when I'm looking here, I have the force of gravity. And let's say we're moving at a speed so that when my car is coming up and running into this wall here, that the wall is going to be pushing me back the same amount that gravity does. Okay, so let's just say these are both 100 newtons. So I have my force of gravity and my force of normal. Now if this were truly the case, and I close my eyes and I feel the seat underneath of me, I wouldn't really know that I was upside down because I just feel normal. I just feel the seat underneath me pushing what it normally did. So we'd actually feel fairly normal if we were at this instant in time looking at just based upon the seat underneath of us and what we feel. So let's say I go a little bit slower. So if I go a little bit slower, I don't jam into the wall quite as hard, and my normal force would be a little bit less than what my normal force normally is when I'm just sitting on the ground and everything's balanced out. So when I look and I ask how I feel, I close my eyes and I feel that the seat underneath of me isn't quite pushing so hard. So in this case, we feel lighter. Let's say I go even slower now. Okay, so I keep slowing down. I'm trying to figure out how slow can I go. And at some point, that normal force continues to decrease until it hits 0. And when the normal force is equal to 0, then at that point, I have entered a situation where I don't feel the seat at all. And so that situation is just like when an elevator breaks and the cable breaks and now we're falling with the elevator. We feel weightless when there is no normal force. We don't feel the seat above us at all. We just feel weightless. So if we're going the right speed in this roller coaster, as we start to fall, because we're moving horizontally also, the car is going to fall with us as we come down, and we're going to be able to stay in our car. If we go slower than that, we go any slower than that threshold speed, then what happens is we'll actually enter free fall before we start falling back into the loop again, and we won't make it around. We'll fall out, and the car will fall. This is why in a roller coaster they have the tracks going both ways, so that if you start to fall on accident, you don't have enough speed, you'll roll back down the side rather than fall out of the car. And so we can feel normal, we can feel lighter, we can feel weightless, and then if we go super, super fast, what will happen then is that we jam into the wall up at the top even harder than we normally do. And so we have our force of gravity, we have our force of normal, which is going to be even greater. And whenever the force of normal is greater than what we normally feel, then we feel heavy. We feel jammed against that seat. So the loop is really interesting because you can really feel everything. So this brings up an interesting discussion. As we're starting to talk, getting into Newton's law of gravitation, before I even talk about gravity, let's say we're in a spaceship in deep space, and the spaceship itself doesn't have very much mass, but we want to simulate what we feel on Earth. So using the principles we just talked about, if I have my little man here on the spaceship, if we're not moving at all, we're just going to be floating around at random. But if I could get this spaceship moving fast enough, okay, so I'm attached to this thing and I get this spaceship moving fast enough, what can happen is that I will start to run into the sides of the wall if I'm also moving. So I hang on to this thing and I get moving fast enough. If we get to that threshold speed when the force that we push out on the spaceship and the force the spaceship pushes back on us, we feel that normal force from the spaceship. If that normal force from the spaceship is equal to what we normally feel on Earth, if it was that same value there, then we would actually feel normal. So if we got spinning around fast enough, plastered against the side of this spaceship, we could actually just walk around here and not even know that we weren't on Earth, because the normal force, what we felt underneath of us, would be the exact same force that we normally feel walking. So this is a very interesting application of this idea, and I hope that this was a helpful way of summarizing the bumps, dips, and loops challenge. I hope it was helpful.